Good morning. Uh, all right. One second, guys. I will be. What will I be doing? I forgot. Sharing my screen. All righty. All righty. Clean. Pop out like that. And you're ready for some math. Okay. Let me just share my screen. Okay, you guys should see that. Yeah. This one. Okay, good. And the music should be here. Pin the music. Fine. And then where's the pop? Okay. We are going to be doing these questions today. So it's about 2:29. Okay, this question I have not done. So we'll also do this question a little bit later. Generally speaking. Okay, here you go. Yep. This is actually pretty nice. What we'll do is this big timer here. I hope that you guys see it. Or Christine specifically. It's pretty hard to see. Yeah, that's fine. do see that's not bad. Not bad. We will solve these. Pretty sure that we actually have not done any of these. And so if we can go through this, it's going to be pretty good. Okay. This question. Prove that between distinct irrational numbers, there exists a rational number. In the sense, what? What's distinct? Like pi and e? Pi. Prove exists. Pi. Alrighty. And e. I'm guessing somewhere between 2.7. And in between that, there is a 3. So, does that prove it? I don't know. Are we done here? That's all I can think of off the bat. Alright. Prove that between any distinct irrational numbers, there exists a rational number. Okay, am I? Suppose. Okay, firstly, can we express an irrational number? Like you know how like a rational number, you define a rational number, right? As in like sum p over q, and that's in z. So my first bet is I'm going to search up how can I define mathematically a rational number. Right? My guess is a real number x is irrational if there exists no integers p and q. So that x is p and q. We could express it like this. So this is their idea of what could be a way to express an irrational number. So there, we call it an infinite simple continued fraction. Okay. And that's expressed as a0 plus 1 over a plus 1 plus 1 over a plus 2 plus 1 over a plus 3 plus. Okay, that is mad weird. Okay, I get it now, right? It's like, I mean, we could use 3 as an example, like 3 over 1, and then is between some type of number that's like 3.0 infinity, like, like a very weird 2.9999, and these are finite, okay? 8, 5, 9, like, so that goes on forever. And then also from the side, could we use some type of related, you know? What makes an irrational number distinct? An irrational number is distinct from rational numbers because okay, maybe we could do something about this. This is sick. Because root 2 is expressed as 1 plus 1. I'll get some space out. 2 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus dot. Okay, there's dot here. But I'm assuming that you could do like 2.001, right? I mean, no, because this is going infinitely already, so. But we could go deep. No. Yeah. Those are some initial ideas. Maybe there's something we can minus. Or we can subtract from both sides. Maybe something about the floor and ceiling. Maybe. What comes to mind. Maybe this is the answer. Okay, this might be it. The floor and the ceiling is part of an integer, and integers are subsets of real number. Yep. Alrighty, that pushes us in a little bit more. Right, we're looking at the ceiling of this and the floor of this, and so we'll always get an exact value. Anything we can think of? Okay, we can talk about this. Okay, suppose there are two distinct irrational numbers. Then okay, what if it's like 3.1? Oh yeah, that's fine. We can use the information that we had before. So I just did a proof earlier about this one. Terminating of decimal expansions and long division property. So this is a very, very sick number. You can see right here. How do I use this one? This is pretty sick, eh? Okay. What I'm saying right here is this part specifically is it's like this part can always be expressed in the sense that whichever n is and whatever decimal it is, as long as it's non-repeating and we know the n number of digits, and if we divide it, we multiply it. Basically, we multiply it to 10 to the n, and then that can be expressed as an actual fraction. Yeah. Here, probably multiply something like that times 10 to the n. Yeah. So with that information, we're gonna go back, and then we're also gonna write something like the existence of said number. Here. Right? So if we were to get two irrational fractions that, let's say it was 3.14159 and then 3.14601.98, and then carry on. Then there still has to be some number here that's like 3.141560. You know, that can be expressed itself as 31416 over 1, 2, 3, 4. So 1,000. Sorry, 10,000, something like that. Okay. So we have something that we can use. Suppose there are two distinct irrational numbers. How do I express that finitely? Well, I know this number is it can be expressed as there exists like an n, which is 0.A1, A2, A3, all the way to AN. Right? And this is and it has to be it has to have B1, B2, B3, all the way up to BK, and then we're gonna find it. But what I mean is these guys have A, B, C, F, G, H, I, J, K, L, L, M. Let's make this M. L, M, N, O. We'll make this O. Right, is equal to A1, A2, A3, to A, or it's never ending. So how could I express this as never ending? I could just express it like that. So there is no end. I just have to write like that, right? And then O, similar, is that. And so we have something like this. Could I divide by... Okay, intuitively I get it now, but I don't know how we should be thinking about how to get this thing out. I mean, not only exists, but like infinitely many irrational. There are infinitely many. I know it is. Are there infinitely many rational numbers between two distinct irrational numbers? Yes, there is. Yeah. Okay, we're on the race step. Let's call this M's, because these are different numbers. Sorry, O's. Right, and these are never ending. Okay. Right now I can write a little bit bigger proof. Could I use this? But these are for simple continued fractions. Like, so this might be one form of an irrational function, right? But not for any distinct irrational numbers. And so then we can define M and O as M is equal to M1, M2, M3, or I think I should write dot. I mean, it doesn't really matter. Yeah. And O as O1, O2, O3, where digits are okay. Never. Basically, we're just gonna know here. Never ending. Never repeating. And by the way, we just have to prove existence. And so the first way that we're gonna push into the proof, I'm assuming, is using the definition of the floor and ceiling. So the definition, let, okay, then it must be that, okay, this is still a generalization, right? That that one is larger than the other. Okay, well, let's suppose that M is larger than O, M is smaller than O. Okay, then here's the first, I mean, if they are at least one integer apart, or if they're at least okay, I don't know how to say this, but okay. Case 1. So in the case that, okay, I have to explain that there's basically, I can just guessing there's 2 cases occur where M1 and O1 are the same, right? So how do I say it like that, you know? I mean, like, at 3.1 and 3.2, there exists like a 3.15. Okay, I guess we can't do floor. Yeah, we can't do floor, but we can try to explain to say this case is gone. Okay, if m is smaller than 0, I is smaller than O. Then it must be that there must be a finite sequence. Ooh. Then there must be a finite sequence. Oh my god, am I cooking this proof? Let's call it A B C D F G H I J K L N O. N equals A1, A2, A3, all the way up to AN. That differentiates the irrational numbers. Okay, I haven't but basically we've made our way into the proof one way or another. Yep. Oh my god. Right? Then there must be a finite sequence that differentiates the irrational numbers apart. We can just call that where AN is the number of digits that are the same between M and O. This is the harder case, right? I mean, if M and O are more than length 1 away, we can simply and is we can simply find the ceiling. So M and floor O, and we get some N that let's just take Q at that differentiates the irrational where AN's number of digits between M and O. Then and since N is a finite sequence, finite number with a terminating decimal sequence, we can express n as, right, our 10n times a1. Oh, I see. It's 10. I think it's 10 minus n. I get the idea. If you get the idea, you get the idea. This is 10 minus n. I'm a dumbass. Hey, okay, that's fine then. Right, because we got 0.1, then we multiply by 1 over 10, we get 1. So 0.15135 times 1 over 1,000, you get 135, right? So, and that works with just like a, you know, and it's just over 10 to the 0, right? Yeah. But we're looking at a number that has a terminating decimal sequence. So then again, I have to still talk about decimals. There's decimals. Okay, so where is the number of digits that are same between m and o? Since n is a finite number with a terminating decimal sequence, we can express n. So let's call it nd, you know, n decimal sequence, nd. So okay, so there's 3 parts. Jesus freaking Christ. No, there's 2 parts. We'll call it number n is equal to n1, n2, all the way up to nn dot. Right? That differentiates the irrational numbers apart, where where a1 to an, where a1 to an is the number of decimal digits, are the values of decimal digits that are the same between m and n. Okay? Then since n is a finite number with, right, so now we've kind of unpacked a big ass number, right? Any 1,900,000 dot infinitely, we have been able to kind of encompass in this number and these numbers. We can express n as our initial n1 to n, right? Plus, is it plus? No, it's dot. We get our 10n, and we get our a1 all the way to an. And that can be expressed as a as a rational number. I'm pretty sure that's it. That was a pretty fun proof. I hope we get it. So now what I would do is I'm sending this straight to ChatGPT actually before we watch the answer. Actually, I really want to pull up this. So what I'm going to do is I'm going to take a photo on our laptop here, on our iPad here. Sorry. I'm going to take this photo. But, sorry. Where the heck did that? Oh! I actually have no clue what just happened. We're going to take a photo of this. I want to read it to ChatGPT because I can't be bothered to. Okay, let's go. Hey, ChatGPT. Oh, fuck me. Hey, ChatGPT. I was the question that the proof that I'm trying to prove is that I'm trying to prove that between the two distinct irrational numbers that there exists a rational number. And so the way that I went into the proof was that I tried to kind of define each irrational number as m1, m2, m3 ... with a never-ending sequence, and then O is also O1, O2, O3 ... as a never-ending, never-repeating sequence. And I mean, decimals or not, or integers or not, that's fine. But then I'm saying because they're never-ending, it would be clear that there must be one that is larger than the other, right? And so if we're just going to compare M1, M2, M3, M4 up all the way up until a point where that does happen, we have a clear divider of two distinct numbers, right? So generalizing that, we're still chill. And then what I also said was there must be a finite number. I mean, then there exists a finite number n that we've just basically found, right? N1, N2, N3. I also added a decimal there, A1, A2, A3, up to AN. And so N1 to NN and A1 to AN, basically, I'm just trying to express it as some type of number with a decimal expansion. And then going right back into what we've basically already proved this evening, that I could express any terminating decimal sequence as a rational number. And then I also wrote at the end as just like as another case, if m is smaller than 0 and more than one length away, there's just the easy way to find that, which the ceiling and the floor of Sorry about that, guys. That's just a slight problem. There you go. We're back. Let's see what chat has to say. Your strategy is on the right track, but it's not rigorous enough to count as a complete proof. The key issue is you informally argue existence of a finite truncation without formally guaranteeing that this truncation actually lies strictly between two. Okay, representing irrationals via infinite decimal expansions is noticing that two distinct real numbers must differ at some finite digit. That's great. And using finite truncations is correct. You did not rigorously prove that your constructed finite decimal n satisfies m is less than n is less than 0. Explicitly construct a number between them. Prove it lies strictly in the interval. Oh, sick! Okay, Archimedean. Never mind. Okay. What the helly? Yes, I agree though. I could have averaged it out. Using density of rationals via Archimedean property. Choose an n in the natural numbers such that 1 over n is less than b minus a. Holy shit. If you insist on your approach, here's how to make it correct. Let a equals 0. Okay. Since a is not equal to b, there exists a first index k where ak is not equal to bk. Yeah. Let's vlog. Okay. Then assume that I'm guessing vlog is like it's like without losing generalization. Without losing on generalization, we assume that AK is less than BK. So we can construct Q as a number 0, then we can argue that Q is larger than A, and then Q is larger than B, because at digit K, we are still smaller. This is a lot better. Archimedean density. Okay, I just want to... What is this? It refers to a standard proof technique that uses the Archimedean property of real numbers and that rational numbers are dense in R to show that between you there is a rational number. For any real number x is larger than 0 that exists in an integer n such that 1 over n is less than x. 3. Cool, sick. We need two real numbers, a, b, there exists a rational number q. So that's basically like the definition. Oh yeah, let me complete my proof first. get the idea. Let A and B be rational. And so two distinct irrational numbers. Then A let's assume we say then A is not equal to B due to never ending, never repeating decimal expansions. There is wait. A is defined by 0.A1, A2, A3, and B, B1, B2, B3. But there exists a point where K is less than BK, where K that's fine. Then let Q be 0. What did they do? Plus, add it in half, right? Okay, that's fine. Just use A, because why not? Yeah. Let Q be Q is equal to 0.1, 0.8, A2, A3, all the way to AK. Then Q is rational due to truncation, finite truncation. How do I say that? Since truncation increases if digits continue. Okay, then it must be that Q is larger than A because What if I did AK plus 1? No. Due to truncation. I don't know how to rigorously say that. Okay, I'm gonna read it. Say it. Yeah, it's not greater. Yeah, I have to. Yeah, K plus 1. There you go. Yes. Okay. So this is the next digit. Yes, this is the next digit. It must be that cute because Q is now AK plus 1 larger. No, it must only be AK plus 1. Larger than. So that is a sum 0.A1 to A 0.0 AK plus 1 larger than A. And that Q is larger than or equal to B due to B being at least AK 0. AK plus 1 larger than A. Because Q is a terminating decimal. Q can be expressed as a rational number due to we don't need to. So here exists a rational number between two distinct irrational numbers. Okay, we have good. I like the proof. Okay, let's see what ChatGPT has to say. Right, why is it thinking right for times? Oh yeah, it's fine. We wrote it like that. No, I wrote exactly that. Ten to the K. Since Q and A agree up to digit K minus 1, but differ at digit K. Sure. Since Q minus A is larger than 1 over the difference. Right? Created, yeah. Created by the AK plus 1. And B minus Q is larger than or equal to 1 minus 10K. Yep. That's fine. Thank you. Now explain Archimedean and dense. That's pretty sick. Yeah. So it's using basically the idea of an arbitrarily small number epsilon. And he's saying that there's going to be a number. Let's say I give you A and B. And B minus A gives some difference, right? And so yes, they are irrational, but also yes, by Archimedean, we can express B minus A. I mean, we can always find a number n that's less than B and A. So find A 1 over n is an arbitrarily small number. And so arbitrarily small is uncountably small, whereas B minus A, chances of being arbitrarily small, it's like oh, fuck. I don't even know how to, you just gotta think about it for a minute. But 1 over n is an arbitrarily small number. And so we have our first inequality. And our second inequality is that if we apply this number over B and A, we're trying to zoom in on that specific point, right? So let's say is 0.5, 5, 8, 9, 7, 4, 3, 2, minus and here 1, 2, A is less than B, right? A is different from B without losing out on generalization. A is less than B. B minus A is some difference for Archimedean's property. 5. I'm just going to show you something. Show myself is equal to 0.589742129. So we can apply our 1 over a gazillion. Over this number, right? And so we get an extremely small number. So that's 1 over n is definitely less than the difference here, which is probably like 0.0, 1 0, 2 zeros, 3 zeros, 4 zeros, 5, 6 zeros. Right? And this one goes forever, and then this one goes to k. If you know what I'm saying, this one goes to some finite point, whereas this one is arbitrarily small. Right? Such that, okay, I'll just write this, make it nicer. Because I really want to emphasize the size gap so we can get it basically right. And so if we apply this on this number, right? We're just gonna visualize that's the difference. we're gonna use this inequality. Hey, we're gonna use this inequality right here. Okay. We're gonna apply it onto each inequality. And so we get NB is, sorry. Yep. No. Cancels. We get 1. What do we do with the 1? What? No, I was getting what they meant. Okay, let's just add B to one side, A to one side. 1 over N. What? You lost me. Yes. Cool. Then why the fuck did you write it like this? Sure. Yeah. Right. I mean, we're basically scaling with like a billion or some big number bigger than that, bigger than the difference of these two numbers. And so right. And so we have something here now. So now there exists an integer k that is within NA and B, which is pretty sick the way they wrote this. So you divide both sides. Then A is where k over n is some rational number. That's pretty sick. That's pretty sick. That's pretty damn sick. We're gonna watch that together.
And it says prove between any two irrational numbers.
Alright, let me actually do it on here. Alright. watch them.
Many of them, but I want to show how to construct at least one rational number. And at first glance, this is quite a difficult problem. If we think about it on the real line, so we draw a little picture here on the real line. So I've got two numbers, I'll call them alpha and beta. So alpha and beta are my two irrational numbers. And I've got to somehow find how to construct a rational number, that is one I can write as a fraction, as a quotient of two integers, in between the two of these. And of course, by the way, these two numbers, alpha and beta, might be extremely close together. The difference between them might be less than, say, 10 to the minus 20. They may be very, very close together. Their decimal expansions might be very close, very similar. So the first thing in this problem I need to worry about, I've got to find out how close these numbers are. I've got to get some measure on how close these numbers are. So let me do some notation. So let the irrational numbers be alpha and beta, and we'll take alpha strictly less than beta. So I want to measure how close these are. So I'll do that. So let D be beta minus alpha. So D is measuring how close the numbers are, and D may be extremely small. If it's big, well, if this distance is, say, bigger than 1, well, I can always squeeze an integer in between them, but the distance may be very small. So the idea is that I want to push these apart somehow by sort of magnifying the picture up so that there's enough room to squeeze a whole number in between them. And I do that as follows. So I let D be the difference of the two. So I'm going to take an integer n, in fact I'll take a positive integer n, such that nd is bigger than 2. And in fact, I think I'm going to, and when I look at it, I'm going to in fact insist these be positive.
It's a weird ass proof. Must be bigger than 2. N times the difference is larger than 2. I mean, basically what we wrote, right? So what we wrote was like, I don't know. Let n d, where d is the difference between beta and alpha, be larger than 2. So n must be some big number. It has to be huge. Right? He was talking about how d might have been some number 10 to the minus 20, right? So 2.5 times 10 to the minus 20. And so this number has to be like that much bigger. Okay, I don't know why he would choose 2. Because intuitively, it's just like very not textbook.
positive, just enough. I haven't got to worry then about negatives turning up. So I'm going to take the irrational numbers both to be positive. If one of them's negative, well then it's easy, 0 lies in between, and if they're both negative, well you can shift them onto the other side and make them both positive and repeat the argument. So I'm going to insist that they're positive.
Yeah. So it's just taking out all the easier ones, the ones where they're negative and positive, the ones where they're both negative, and the ones, what do you say?
To the other side and make them both positive and repeat the argument. So I'm going to insist that they're positive.
Yeah. And the ones where they're, let's say, distance one away from each other, so floor.
And that'll avoid any technical problems. So D is the size, is the difference between them. I take an integer, n, so that nd is bigger than 2. I could have made this 1 actually, but I may as well make it 2 just to make the point clearly. Okay, let's hold that thought. And now what I'm going to do is I'm going to use this n.
If he used 1, it probably make people like people would follow along, but that's even
to magnify up these numbers. So I'm going to multiply both of these by n. I'm going to multiply both of these by n. So now consider the numbers n alpha and n beta. And I want to look at what's the difference between these two. So when I look at n beta minus n alpha, I have n, factor out n beta minus alpha, that's nd, and that's bigger than 2 because that's how we made it. So that means the gap between these two, that distance, is at least 2. And if it's at least 2, then I can squeeze an integer in between them. If that distance is bigger than 2 units, then I can squeeze an integer m in between them. So,
yes, but
there is an integer, and it's important that I'm taking these as integers, m, such that, from my picture, n alpha is less than m is less than n beta. So I like to think of this as like taking a magnifying glass. You magnify this up by a factor of n. That makes the difference between here at least 2. Now I can pop an integer in between. And finally, for the last bit, I take the magnifying glass away and I divide everything through by n. And so when I pull the magnifying glass away, i.e. by dividing by n, then in here I'm going to have m over n, and that's a rational number in between them. So dividing by n, hence alpha is less than m over n is less than beta, and m over n is a rational number. And that's the end of the proof with that in that problem. So that's an interesting problem, that between any two irrationals I can squeeze a rational. In one of the other problems you'll be asked in the tutorial problems, I think it's question 42, it does sort of the other way around. It shows you, and it's easier, and it shows you how between any two rationals you can squeeze an irrational number. The interesting thing is that you can squeeze, in fact, infinitely many rational numbers in between any two irrational numbers, and you can squeeze infinitely many rationals between any irrationals between any two rationals. But that's all I want to say on this problem.
Pre-ChatGPT, be creating some really good students. Post-ChatGPT, studying. Please quote me. I guess you alright. Okay, that's off. That's the hardest question in here. The question took us an hour 30 minutes. Yeah, so okay, this question, I mean, I vaguely read at it. I'm not too sure what it means, so I want to read it again. Today I've been writing pretty good proofs. Don't know why, things just started clicking. Yeah, really like writing the proofs today. Very nice proofs. This was a really fun one. And they were all about decimal expansions. So, which is why it gave me the intuition to get to this other one. Oh, that's what he was saying. Okay. So for anyone who's watching, this question is question 24, and this question is question 30. But in the old problem set, this question came after. I feel like if you had this question, it'd be a lot easier. It would be a lot more understandable. Yes. So I think we were doing from oh, this was good too. We've done about 14. Yeah, we've done about 14 questions. From 15 questions. Sorry, we've done 15 questions today. Actually, no, excluding these. These are hard questions. I'll come back to them after. Or preferably like one question per day. Each question that has a star takes about an hour to really dissect. Yep. Yeah. So we've semi gone through them, and so I'm not too worried. And this question is an assignment question. I'm not too worried. I think this might be my second and last question of the night. That means I'll be 10 questions behind. I have not done proof of contradiction, and school starts tomorrow. Actually, no. Okay, I'll do Mobius numbers. I'll do a little bit of that econ work, and for now, I should be doing. Yeah, my bad. Econ investments here. Okay. By definition, a sequence of numbers u1, u2, u0, u2 into infinity diverges to infinity if and if for all n. Okay, m is a of numbers in the natural system, there exists an n in the natural system where all of n is larger than n. And u of n is larger than n. Okay, we're correct. What is math, bro? Math is not working. But if a sequence of numbers u0, u1, u2 diverges to infinity if and only if for all m natural is 0. I mean, let's just like dissect this problem, right? Set n, right? So 0, 1, 2, 3. There exists an n here. So there exists an n. There exists a set n. We should do that. there exists some n in the set M. Sorry, it's not finite. It's not finite. It's not infinite. Yes, it's not infinite. Because it's only converges to infinity if un is larger than n. So 5, 7. There exists some n also. And then this is the part where I'm very like for all n, which is this. For all n larger than the set n, where all n is larger than set n. So the value of n is larger than all elements in set n, and that Q is larger than n. So many equations. Sorry. No stuttering. Show that the sequence diverges to infinity. Plug something into that. Yeah, for this question, like proof of calculus, continuity. I think we have something for this. The quality of the iPad will get a lot better because I bought the HDMI video capture card, and so we'll be streaming, and it'll be a lot nicer than Discord streaming. let's just write it into sentences. For all, so there's a set M, and all numbers in set M are natural. Right? Done. So that's 1. Because it's a increasing. That probably implies increasing, or sorry, a second sequence. Okay. There exists a set in the natural numbers. There's a set N. There's a set N. Also natural numbers. Such that this part bugging me out. Yeah, there's also the N, and all numbers of this value N, all values of r small n is larger than all values of set N. I'm just going to ask ChatGPT some questions. So we're just going to read to ChatGPT. Hey, I'm just... Hello? Question about sequence of numbers, but I'm just... If they've given me a statement that says all small n is larger than set n, and then they give me an equation for n, that's just how it is, right? That's just like all values of n are larger than... Let's see. Let's just see. Is it larger than set n or all the values in the... Yeah, not answering anything because I probably didn't ask the right questions. Just all values of n larger than all elements in set n. No, if it's for all n is larger than set large N, then does that mean it's the n values are larger than the... I'm assuming it's larger than all the elements within set n. Yeah, probably. All elements of un are larger than, so all values of un are larger than set are all elements of set M. So there was a sum statement somewhere. There exists a set where all values are larger and all in set N. These are perfect squares. What are we looking at? 1, 4, 9, 16. For all M in the natural numbers. So you gotta start with 0 as well. There exists a set N also in the natural numbers, such that for all N that's larger than set N, then you wait. Why? But it's like this one converges because it's all natural numbers up to infinity, but then un just travels faster. Right, so it's like the natural numbers on steroids. Or no, because this is a finite set. For all values of set M in the natural number system, there exists a set N in the natural number system such that if all values of N given by the equation, the sequence given by un is equal to n squared, is larger than the elements within set N, then un will be larger than set M. So how do I show that? Let's let a sequence u0, u1, u2 diverge to infinity. That's fine. Then given by un is equal to n squared, diverge to infinity. Then oh, okay, wait. for all elements in set N. Okay. Okay. This is not the idea. This is just a set. But we know this set implies it's a finite set. That's one. Number two, set N is the one that we want to talk about. Has elements. If and I think this should be after. Yeah. Let there be a set M in the natural numbers. And existence of set N also in the natural numbers, where for all N that's larger than the set N that UN is larger than elements of set M. Just don't know why. I mean, if I put this as like 3 million, and that's my set. What could they do about it? Oh, okay. Then N has to choose one of this guy. There exists a set N that encompasses this, right? And then N has to be bigger than that number. And so N squared is equal to that number squared. And so it's larger than M. So yeah. I'm cooked. Yeah, I think. Yeah. No, for all values of N that's larger than M. For all Okay, for all values taken from set M, they are hence squared. Larger than elements of set M, hence they are squared. So this is a positive ascending sequence. Let un be n squared. Let m yeah, I'm good, bro. I will read the. I will think about this when I sleep. I will not chat GPT it. I will think about this when I sleep. Okay, good night, guys. It's been 2 hours. I'm gonna go to sleep. Okay, thank you.